Good morning. My name is Guangwei Huang from Almond board. I basically wanted, thank you for taking the time to attending our webinar. This is our ongoing webinar offered by ABC based on our research results. So this session is about alternative harvesting. We're trying to provide update information from our research project related to harvesting. As you all know, ABC have a goal to reduce the dust during harvest by 50% by 2025. So we are looking at the alternative harvesting. So this webinar is really invited several presenters, include Dr. Chris Simmons presenter from UC Davis. Dr. Chris Simmons is going to talk about the technical economic analysis his group carried out for us, and then followed by Patrick Brown, work on a couple of projects in terms of how look at the pros and cons of harvesting, and then followed by Zhongli Pan and Irwin and Dr. Gonzalez, look at the different ways for drying in fresh in-whole almond, because drying is a bottleneck for look at any alternative harvesting. But our goal is trying to provide you update information about what we have learned about the alternative harvesting, what benefit they offer, what the issue we had to address. But definitely there is some benefit from the alternative harvesting, but also we had to prepare. It's a long-term commitment. So I will just give the control to Dr. Chris Simmons. Each of them going to present after each other. So first, Dr. Chris Simmons, followed by Patrick Brown, and then followed by Dr. Zhongli Pan and Erwin Gonzalez. Okay, I'm going to give control to you, Chris.
All right, great, thank you. Is everybody able to see my title slide?
Yes, you want it.
Okay, fantastic. Well, good morning, everybody. Happy to tell you about the work we've done for the techno-economic assessment of off-ground harvesting. In this assessment, we're comparing baseline, which is the harvesting practices that we're all familiar with in terms of mechanical shaking and blowing and sweeping and pickup, to several alternative scenarios. And the animation will give you an idea of the 3 scenarios that we compared against this baseline conventional harvesting scenario. So as we know, for conventional harvesting, there is passive drying on the floor of the orchard, and there are certain operations that create dust, and there are drivers as a result to explore these alternative practices. Now, one alternative would just be to do mechanical shaking, the shake and catch, and then at that point, just deposit the almonds onto the floor of the orchard to passively dry. In essence, you're just bypassing the blowing and sweeping step. Another option for off-ground harvesting would be to do the shake and catch and then transfer the almonds to a dedicated drying lot. This would be adjacent to the orchard and would perhaps be prepared in a way that allows for very dense drying and minimal dust as you operate in the dedicated drying lot. We may also actually see improved drying kinetics because there's no canopy to shade the product at that point. The final off-ground harvest scenario that we considered was mechanical shake and catch, followed by transportation to some third-party facility. This would be a facility that has the ability to do mechanical drying of the almonds, and this could be a dedicated drying facility or a huller sheller that has drying capacity on site. So comparing these different scenarios, just to give you context, we're assuming a hypothetical farm that's 100 acres. It's a mature orchard with a 2,200 pound per acre yield, 1% windfall loss, and then using conventional practices. These would be the practices that are captured in the ANR cost studies that are provided for different growing regions. So the heart of the techno-economic assessment is that we consider all of the different cost inputs and how they change across these scenarios, and predict their impact on the net return per acre, so the change in profit for the grower per acre. And we're capturing several effects that we expect to happen as a result of off-ground harvest. One of those is that we're avoiding or displacing some operations in the field. At minimum, we would be displacing blowing and sweeping, and depending on the format of off-ground harvest, we may also be avoiding pickup, and there's a cost benefit that goes along with that. By avoiding the need to have almonds on the floor of the orchard in certain scenarios, we are also potentially adjusting the cultural practices in the orchard and decreasing the amount of pest control that's needed, less stringent weed control, no ant control needed. And so again, that would be a predicted benefit to the grower in terms of inflating profit per acre. But it also goes the other way, because in off-ground harvest, if you have windfall, then you're not going to be able to reclaim those almonds because there's no blowing and sweeping step. So there's the potential to have a new loss through windfall. And then one of the unknowns right now is really what is the capital cost for the shake and catch harvesters, relatively new equipment, haven't been operated over a complete lifespan yet, so we don't yet know the full cost to maintain and repair those. But in our analysis, we made some assumptions on the capital cost based on the existing capital cost for conventional mechanical shakers. And we ran the techno-economic assessment under these three scenarios. So I'd like to run you through some of the results, starting with scenario one, which was that scenario where we do shake and catch, but then lay a windrow of almonds in the orchard right after that. So if you look at just that base scenario, there is a small cost benefit just due to bypassing the blowing and shaking step. But if you were to try to modify the soil to decrease dust generation, for instance, if you added some type of soil stabilizer, and there are food safe stabilizers on the market, if you were to try to incorporate that in the entirety of that orchard, you would see a dramatic decrease in profitability. It's too large an area to try to stabilize the soil. However, if we go over to scenario two, which is the use of a dedicated drying lot, we see that across different permutations of this scenario, there are predicted benefits to the grower in terms of increasing profit. Here we've looked at three different sizes of drying lots, a 5, a 6, and a 7 acre lot. And if that dedicated drying lot is just bare soil, we do predict an increase in profit for the grower. And that, again, stems from the fact that we are bypassing the blowing and sweeping. We're doing ultimately pickup on a smaller area, a 5 to 7 acre lot instead of an entire 100 acre orchard. And we can consider different dust mitigation efforts that could potentially be used on this drying lot. For instance, if we were to lay a tarp down, it would decrease the improved profitability, but we would still be predicting a net benefit to the grower. And if we look at a more robust tarp, and nobody really knows how well a tarp would stand up to a pickup machine, so maybe we need a thicker tarp. And again, this is a tenable solution for the smaller drying lots, but begins to become untenable for the larger lots. And so too with these additives to stabilize the soil and prevent dust generation. Depending on the size of the lot, we either maintain a predicted profit increase for the grower, or we erode that in the case of a larger lot. The other thing to consider here is, where does the land from this drying lot come from? For the data presented here, we assumed that the grower could carve out some marginal land that they already own to use for the drying lot. But if the grower had to lease new land to accommodate the almond drying, then basically all these data points get shifted over to the left, because we now need to incorporate the increased cost of leasing that land. So you can see that there are more soil stabilization strategies that become untenable, but several of them still remain as predicted to yield a profit increase for the grower. The other thing to consider is tuning the size of the drying lot to the yield of the orchard. You can see here across a variety of lot sizes as compared to the orchard's yield, and then considering the different soil stabilization techniques. There's a diagonal here that shows that threshold for when this process would be predicted to improve profits for the grower versus when it would be detrimental and decrease profits for the grower. So as you might guess, having a large drying lot for an orchard that has poor yield yields a detrimental effect to the grower that is compounded if you then add in the costs to stabilize the soil in the drying lot. So this gives you an idea of where that threshold exists in terms of what lot sizes and soil stabilization techniques would be viable given different yields in the orchard. The final scenario is the mechanical drying scenario where we shake and catch and transport the almonds to a drying facility. In this case, the primary variable that dictates how profitable this change would be has to do with the fact that in this scenario, we are now hauling almonds that have not been dried. So there's an increase in mass to be hauled, and that affects the cost of hauling. So we can look at how the change in profitability will be affected by the moisture of the almonds at the time that they are harvested and hauled to the drying facility. So you can see here, anything above 24% moisture, the increased cost to haul that would offset all of the cost reductions that we had on the pest management side, on the decreased blowing and sweeping and pickup side, and we would not predict a benefit in net returns to the grower in that case. But for most reasonable initial moisture contents, we still do expect to see a benefit to the grower. So that gives you a high-level overview of some of the predictions made by the techno-economic assessment that can help to guide decision-making for growers that may be considering a switch to off-ground harvesting, and maybe weighing the benefits of having some type of dedicated area on site for passive drying versus just shipping the almonds off for mechanical drying. But there's still some questions that we need to know to refine this analysis, and this is having to do with the true cost of these new harvesters. How do they depreciate? What is their efficiency? What is the cost in terms of operating cost to maintain them? And then what will be the state of mechanical drying if and when off-ground harvest begins to scale out? There's a very small bandwidth and capacity for mechanical drying now. Most of that is in the Sacramento Valley. But if this were to become a viable option for many growers, we would need to scale out drying capacity. And what would that do for the cost of drying? On one hand, we could expect an economy of scale, and the cost of drying would go down compared to what's offered currently. On the other hand, if many growers switch rapidly to off-ground harvesting and the mechanical drying capacity doesn't keep up, then the cost of drying would skyrocket. So there's a question of how much the drying capacity is going to keep pace with the adoption rate for growers switching over to off-ground harvesting. And then because one of the benefits of off-ground harvest is dust mitigation, there needs to be more work to actually quantify how much dust is reduced under each of these scenarios so that we can align those benefits with the economic benefits. And with that, I want to thank you for your time and look forward to your questions later on in the webinar.
Some of the pros and cons of alternative harvesting. As Guangwei and Karen and Gabrielle will know, I've been beating this drum for a long time, and I really do believe there's a lot of benefits that go well beyond merely the dust mitigation. Next slide. Okay, so you've seen beautiful cartoons from Chris Simmons. What I'm going to look at here is the second sort of scenario where you shake and catch, that is the fruit not hitting the ground during the harvest process. As I've analyzed this possibility, it really becomes clear that the real benefit, or one of the big benefits from alternative off-ground harvesting, is the ability to do an early harvest. By early harvest, I mean 2 to 3 weeks prior to current practice.
Yes.
And I'm going to show you some examples and some data that illustrates why and how. We have somebody speaking on here. Joseph, can you mute yourself, please? All right. If you could go back one slide. Sorry, Guangwei.
Okay.
Got interrupted there. The early harvest, which is 2 to 3 weeks prior to current practice, actually ends up being a profound benefit. And then, of course, is the mechanical dehydration on site or in a processing plant, which will be discussed by our next speaker. Next slide. So, and you can step all the way to the bottom of this slide, and I'll talk through these. You know, as we've thought about this over the years, there's some very clear rationale for off-ground harvest. Obviously, in the green there, the dust generation, that will be a profound reduction. The fewer passes through the field, of course, mitigates, as was shown previously, some of the costs of the harvest and the labor itself. Some of the very likely benefits of the off-ground and early harvest are reduced insect and pest disease, both hull rot and aflatoxin and navel orangeworm. I'll show you some data about that. We also predict that going 2 weeks early will reduce water stress because you've got far fewer activities in the field that limit when you can get water back onto the trees. Not dropping the nuts on the ground gives you increased orchard floor management, so we can really start thinking about soil health and not having the almost desert-like conditions that we need to have for current harvest practices. So that has a profound potential benefit right there. Improved orchard floor management, the ability to use hulls and shells and organic matter. Once we build these machines, and we have a project starting this year, yield monitoring to get a bit more precise with our management strategies will be possible. And then, of course, not being on the ground reduces food safety issues. Next slide. But of course, there are some concerns and some unknowns. Some of these were mentioned by Chris. What are the negative impacts of excess nut moisture at harvest? Are there problems with nut quality if you shake those trees 2 weeks early? The question of windfall is always forefront on growers' minds, and so we need to understand when and how and why does that occur and what is the quality of those nuts. And if we think about enhancing soil organic matter and soil health, and we're returning hulls and shells or other materials to the ground, we really need to understand how well do they release nutrients. So I'm going to show you experiments and results just very briefly on these 3 topics. Next slide. Okay, the first one, effect of the early harvest, off-ground harvest on hull rot and navel orangeworm. This was a project that was done at 2 locations, randomized complete block design. We managed the irrigation to mimic what would happen in a normal harvest. That is, we would do a dry down prior to the early shake so that the trees were not barked, and we had very good success with that, and then measure hull rot and damage. Next slide. Just one data slide from this. If you look at table 1 at the top, at the Denair site, we're measuring hull rot strikes with the early harvest, which was about 3 weeks prior to traditional harvest, the harvest that the grower did. And you can see we have a 50% reduction in hull rot strikes. This is well understood to occur because the shorter amount of time that those fruits sit on the tree, the less time there is for infection and the less time there is for damage to the tree. In the bottom table, I'm just comparing the hull split that we saw at the 2 harvest dates. At the Davis site, in fact, the fruit were all 100% hull split, but they differed in the degree of hull split. Early harvest had just a hull split the size that you could put a quarter into. Standard harvest was the wide open butterfly. At Denair, you can see we're only at 85% hull split. Everything had a suture. 85% of nuts were open versus the standard harvest. If we go all the way across to the right to the yield, that's the important data. Davis is a young orchard. You can see no effect whatsoever of shaking those nuts off the tree early on yield. So 3 weeks earlier, no negative compromise. Next slide. We also had done this work with Michael Coates, who was in my lab and also from the University of South Australia. This was done at 2 locations, Australia and Arbuckle in 2015, 2016. Basically shows exactly the same data. You can shake those trees 3 weeks prior to what you currently do, and you will not lose any statistically significant yield. Next slide. This is not surprising. You can go back 40 years, or maybe that's, 45 years to 1986. And this was also experimented on. And it shows that nuts, once they've reached that B3 stage, which is that quarter size opening, you have achieved full kernel size. Anything after that is not benefiting the growth or the yield of the tree itself. Next slide. All right, so the conclusions from that: no negative effect on yield. Earlier harvested nuts, of course, had a higher moisture. You can see the image on the right. Whole rot strikes were 50% reduced. Navel orange worm we're still working on. I think navel orange worm is going to be the biggest driver of this, along with the dust, depending on where you are. But the San Joaquin Valley cost studies estimate the total costs you're spending on navel orange worm protection is something in the order of $400 an acre. So if you can mitigate that by getting those nuts off the tree where they are prone to infestation, onto the ground or into an off-ground facility, you have the potential to save as much as that $400 to $500. And not having to mummy shake would be a blessing for so many growers. Next slide. Okay. The second part of the activity is, one of the opportunities for off-ground harvest is that you now have the ability to manage the soil with cover crops or manures or hulls and shells, and change the whole image and change the whole structure of the orchard from that very bare desert-like situation that we currently have to do to facilitate the shaking into a much more balanced and sustainable system. But one of the questions, of course, is if you put materials back on the ground, how useful are they? Next button. So we asked the question in particular around hulls and shells. The reality is the hulls and shells of almond contain 70% of all the potassium demand of the orchard. So if you could return that to the orchard, you reduce your potassium demand of the orchard by 70%. Question is, how quickly do they break down and how useful are they? Next slide. So we did an experiment. This is up in, this is the example of the Woodland site. We have several sites. This was an application of a whole shell mixture from Mariani nut onto the orchard floor, spread across the entire orchard floor. Now we put 8 tons out here. A 3,000 pound crop would generate about 3 tons. But in this case, we spread it over the entire orchard floor to mimic what would essentially be underneath the tree row. Next slide. What we looked at then was just the release of potassium. Now we have other data on nitrogen and organic matter, but I thought I'd just show you the potassium. So on the left, at 2:10 and February 10th, we applied this 8 tons of material. What we're measuring is soil exchangeable potassium underneath the treated or not treated orchard soil. So the red is the non-treated, and all the other colors are treated with either hulls, shells, or hull shell mixtures. And what you can see is quite remarkable. In that first 2-month period, immediately after the application of water, soil exchangeable potassium jumps to 650 ppm when those materials were used. That declines a little bit, that declines over time, but it always stays higher than where you did not apply any of these materials. If you push the button again there, Guangwei, the question is, how does this time with tree demand? Well, that release curve and that decrease over time matches exactly the demand time for potassium uptake in the top right graph. So you have here highly viable potassium source coming out of those shells at exactly the right time following the irrigation in the springtime. Next slide. Okay, big questions on windfall. So a quick analysis of 2 windfall experiments here. The first is, are windfall nuts of good quality, and are they useful, and do they have the same characteristics of nuts that, I should say early harvest nuts, do they have the same quality characteristics of traditional harvest nuts? Next slide. Oh, actually, I should say we did that experiment at multiple sites in a large trial over the last 2 years. Now, as was mentioned by Chris Simmons, in this particular slide, T4 means harvesting 4 weeks before traditional harvest. T2 is 2 weeks. T0 is 1 week. 2 locations, 2 years shown here. Let's start on the left in Bakersfield. Of course, those kernels have high moisture content. If you harvest them 4 weeks earlier, that declines over time, going from the 20% to the 0%. We did the same experiment in Chico, and there's much less difference there. We haven't quite explained why that is. It may have been because of more aggressive grower water management, suggesting that you can minimize some of that moisture in the early harvested nuts with water and irrigation control. Next slide. In terms of no, you jumped 2 slides there. Go back one. Oh, all right, go forward. Okay. One of the questions about windfall, and I'll get to a quantification of how much windfall occurs in orchards of California. But one question we had was, growers are very concerned with windfall, but there is a question that if those nuts had fallen off the tree 2 or 3 or 4 weeks prior to traditional harvest, do they remain good nuts? And just very quickly, that T4, these are nuts that fell on the ground 4 weeks prior to normal harvest. And we see a profound mold and insect damage in those nuts that were on the ground for a long period of time in the orchard. This suggests that they're in fact old nuts that you do not want to pick up because they are a high source of contamination for the remainder of the nuts. It does also suggest that it's that window of 2 weeks early that is important and that we need to focus upon. Next slide. This is some work from myself and Michael Coates and Guangwei, basically showing that once your nuts are within 2 weeks of your traditional harvest, 3 weeks of your traditional harvest, they are 100% full quality. All of their quality characteristics, nutritional characteristics are the same. Next slide. Okay, so just a summary of this. Obviously, earlier harvest, 4 weeks earlier, gives you quite a lot of moisture, somewhere in the 10 to 25% range. We believe there are some management strategies that can help reduce that. In all of the early harvest nuts, 4 weeks, so 2 weeks prior to traditional harvest, disease incidence, quality incidence, size of the nuts are all equivalent. So you don't lose anything in terms of yield or quality by shaking those trees early. Next slide. Now, the final analysis that I want to show you, this has been going on for 2 years, is to ask the question, what about windfall? You know, how big of a deal is it? How many nuts do we lose? How widespread is it in the industry, and what can we do about it? This was a large experiment. Bottom left, you can see the 38 orchards that we used up and down the valley. In each of those orchards, if you look at the panel on the right of the aerial imagery, the satellite imagery, we did a transect of trees and counted the amount of nuts that fell under that tree using that image in the bottom left with 6 different measurement points around each tree. And then you can see the challenge we had in measuring how many nuts are on the ground. You have to count those nuts. So this is a very large experiment. We're still only 20% of the way through data analysis, but I think we can make some conclusions about this. Next slide. Okay, so here is data on the windfall over the 2 years. And the top 2 panels is 2019 and 2020. And this is the windfall of the orchard. So this includes all of the cultivars. The way this is expressed, on the left is the number of orchards. So the height of that bar represents the number of orchards that had between 0 and 3%. That should say 0.3% windfall drop. Then the number of orchards that had the 3 to 5, the 5 to 7, and the 14 to 7. If we start in that top left panel, this is all cultivars in 2019, vast majority of orchards, probably 80%, show a windfall that is in the 0.5 to 0.8% level. So it's not a big deal. 2020 was a more difficult year. A lot of orchards kept nuts in the field for much longer than normal. Shakes were delayed and the weather conditions. So you have a slightly higher percent, but still the majority of orchards, the amount of windfall is quite trivial. If you look in the bottom panels, this is a discussion of nonpareil. Nonpareil is particularly not susceptible to windfall. Almost all our orchards have a very low, less than 1%, 0.8% orchard windfall. And 2020 was a little bit worse, but still, it's uncommon for windfall to occur to a substantial extent in nonpareil. Bear in mind, even though this was 15,000 data points, it was still only 80 or 90 orchard plots out of the hundreds of tens of thousands in California. So we do our very best, but we cannot be exhaustive in this analysis. The next slide. There are some challenges with late cultivars. Monterey in particular, in 2019, 2020, we had some orchards with 10 or 15% of their nuts on the ground prior to the traditional harvest. Still, in general, percent windfall is quite low, but there are sporadic events, and last year was particularly notable. Next button. To summarize that, in the majority of sites in both years, something in the realm of 0.8% fruit drop. Normal wind events in the valley, Sac Valley, North Valley, and South Valley really don't cause much windfall. It is that rare, heavy windstorm event, or the mini cyclones that sometimes go through the fields that are important. But really, what is the biggest cause of windfall is machine knockdown. That is knocking off the Montereys as you're harvesting, the nonpareils, knocking off the cultivars as you move through the field with multiple passes. This is greatly exacerbated by the dryness of those trees. So if you get those trees to full butterfly dryness and you leave those nuts on the tree, then indeed windfall can occur. It can be almost completely mitigated by shifting your harvest back to that B3 2 or 3 weeks prior to traditional fruit maturity. Again, this is not new. There's a study here from Wilbur Reel and Joe Connell, probably about 50 years old, that shows once those nuts reach that 100% hull split, that is the B3, leaving the nuts on the tree anytime after that opens you up to potential for windfall. Next slide. Okay, so just summarization of everything. The early harvest, 2 to 3 weeks, which I think is a key practice in the alternative harvesting regime, has no negative effect on yield or harvest. It absolutely reduces hull rot. We have full expectation, given the biology of navel orangeworm, that will be dramatically decreased as well. It allows you to manage that orchard floor. Hulls and shells, it turns out, are a particularly viable source of potassium for orchards, as well as the organic matter. Windfall does certainly occur, but in the vast majority of cases, it's minimal. If you want to go back one, I know you want to get me finished here, but windfall, it's really those late cultivars, particularly if they're left over dry on the tree, that is the constraint there. Obviously, the early harvest fruit have high moisture. We've got to deal with the drying. There's the other real effects. The benefit to dust have not really been measured. The tree health benefits, the return yield benefits have not been determined. So I'm going to leave it there. Thank you very much.
Everybody, and you just heard Chris and Patrick talk about the potential benefits and also answer questions for the alternative harvest methods. Definitely, when we say take the off-ground harvest method and to replace the traditional methods, then we are going to deal a large amount of the wet almonds that need to be dried quickly. And thank you for the Almond board and supporting the research. We during the last 2 seasons, we have done quite a bit of work and extracted some information from more than 300 pages of the report, and I'd like to share with you, and also wanted to share my thought where this is the mechanical drying may go for the future. Next, please. Definitely, we have a lot of questions that need to be answered if we do use the off-ground harvest. And at the same time, we do know we have a lot of commercial dryers available in the valley. And so the question is, can we use them for the almond drying? And also the question is, can we dry the almonds efficiently without affecting the quality? So we also look for, say, what are the benefits? Can we use this mechanical drying to kill insects and microbes during the drying? So what kind of the cost it could be? Are there any other benefits from this overground harvest and the mechanical drying? So that's kind of what we wanted to answer. Definitely, we have some the information. We don't have a whole picture yet. Next, please. So as I said, we have a lot of the dryers in the valley, and during the last 2 seasons, we tested 3 different types of commercial dryers on the at the different locations, and with the different variety of the almonds and also different drying temperatures. That means from the ambient to the highest temperatures like a 72 degrees C. That's a pretty high temperature. Next, please. In order to find out, what kind of the limit we can push for the drying temperature, we can dry the product quickly without affect the quality, and also to see if we can kill any insects, microbes. We also done the laboratory test using pellet scale column dryer, and also using laptop dryer, what you have seen. Particularly in the laboratory, we pushed the temperature to much higher. And a couple of the tests, what we have done is using like an 80 or 90 degree to dry the almond for a short time. That means get to the almond temperature to 6 degrees C. Then we switch it to a lower temperature to finish up. I will show you a little bit more details later on. Thank you. Next one, please. Definitely, quality is very important. We care about, if this is the overground harvest will reduce the damage from the insects, and what kind of moisture content it could be, how that may affect the drying performance, and also the energy use or cost. So we look at the product color and also the cavity conceal the damage. That is also very important. So after we dry the almonds, we put the almonds in the hot air oven at 135 degrees C for 90 minutes. Then we cut out. What you can see that what's called the color development score, and to see how the color may change. Ideally, if anything below number 4 and the average number is about around 3, that will be a good one. And also we look at the microbial safety. That's mainly related to bacterial and fungal counts. Next one, please. All right, this is very interesting. Just like Patrick mentioned, if we do the overground harvest, we have a good opportunity to reduce the insect damage. From the last 2 years, what we see, regardless of the initial numbers of insects damage, if we use the overground harvest compared to conventional harvest, we can reduce the insect damage from 40 to 50%. And if we look at some of the varieties, they had a really high damage from the conventional one, it's more than 10%. What that means, the reduction for insect damage I'm talking about may be able to pay for the overground harvest and also mechanical drying. Definitely, there are a lot of numbers we need to calculate. We are not there yet. Also, last year we look at the shake the almonds to the top and to see if that can reduce the damage. Definitely, we can see from the table on the right, we see the trend. However, because for this particular lot, the initial damage was low, and statistically they are not significant, but the point to the trend seems as though if we dry the product on the top, also can reduce the damage. At the same time, from the picture, you can see the overground harvest one on the left compared to conventional one is much cleaner. Next one, please. Okay, this is the slide that shows the average moisture of the almonds for the different fractions. Definitely depends on the variety, harvest time. The moisture really varies quite a bit. And also, if we harvest at a relatively low moisture, we see a lot of split hulls and also the kernels. But if we do harvest at a really high moisture, when we talk about around 50% for the whole almonds, we do not see a lot of, say, kernels or the hulls. Next one, please. All right, from this one, what we can see for 3 different varieties, the moisture content in the different fractions. For some varieties, the kernel moisture is relatively low, okay, compared to some of the others. What this means, if we harvest the almond, say at an average moisture relatively low, we can have the kernel moisture at a quite low. That is good. I will get there later. So, next one, please. All right, come to mechanical drying. We did look at, say, in the laboratory. If we use this is a high initial temperature followed by holding and the low temperature to finish up to see if we can kill the insects. And based on all the results, what we've seen, and we could to kill all the insects. However, because the last year's initial insect damage was low, or the number of insects was low, and we wanted to continue to demonstrate and the result and repeat the test for the coming years. Next one, please. At the same time, microbial safety, it is very important. And also when we do this is the overground harvest, if we do not dry it right away, then we want to know if that will be a concern from micro safety standpoint. We look at the total count of the bacteria and the fungus. Those are the figures on the left. What we can see, if we put the almonds in the can, don't dry them for 4 days, 3 days, we do see the second day, the numbers are increased. So it means we do need to dry the almonds quickly after its harvest. On the right, we look at the potential salmonella and also the total micro counts to see if we use a little high temperature drying, we can reduce the numbers. The result is, since there's a trend, we can use a little high temperature drying to reduce the number of the E. coli and the total plate counts. But statistically, we have not seen that something significant because the little limited number of the tests. Next one, please. We look at the quality from color, cavity, concealed damage, and also processed value and free fatty value, and also compare with the conventional one. Good news is for all the tests, what we have done, we have not seen anything significant. So it means all the quality is good. We have no concern about all the conditions we tested. Next one, please. All right, now I think we care about, say, if we use a commercial dryer, how long it may take to dry, and also what the cost could be. I can give you some kind of a general number, but the long numbers I will not go through them. On average, we are talking about probably 5 to 8 hours in that range when we use the temperature, say, around 60 degrees C. That's the number I like to share with you. Definitely, if we use the ambient air drying, it takes too long. That could be 3 or 4 days. In terms of energy cost, On average, I would say probably around 1 cent per pound of the dried almonds. Okay, and definitely, the cost depends on the initial moisture. We rare this. That is will be very little bit, but on average, I'm quite confident about 1 cent per pound of dry almonds based on what we have seen. Next one, please. We also did the test using column drying in the lab. Definitely in the lab, we can push the temperature higher and further reducing the drying time. And particularly if we dry the in-shell almonds compared to the in-hull almonds, we can reduce the drying time by 60 to 70%. That's very significant. Next, please. So it is a very similar situation. So this also shows the column dry result, as I said. And if we dry the in-shell, we can reduce the drying cost, increase the throughput. Okay, next one, please. We did a lot of the calculation to predict the cost and also the drying rate based on initial moisture content and also the drying temperature. Next one, please. So then come to the question, as I said, if we harvest the almond, say, not too early, we have the loose hull and the kernel in-shell, and also the in-hull almonds, the mixture. So what we found, we can use the size, based on the size, to separate the in-shell almond first, then using the technology called the terminal velocity, based on the air velocity or density, to separate the loose hull from the in-hull almonds. So the loose hull, we don't need to dry. Then we can dry the in-shell almond and the in-shell almond separately. That will increase the throughput and also reduce the cost. Next one, please. So come to the conclusion, definitely we see the significant benefits from reduce the insects damage from off-ground harvest. The product is cleaner. We also see we can dry the off-ground harvest of the almonds with a relatively high temperature. What we have seen, there's no concerns, even the temperature up to 72 degrees C. Or we can use a stepwise temperature, means start with 90 degrees C followed by 60 degrees C drying. That can reduce the overall drying time. So in general, if we do use a high temperature, that will increase the energy cost. That's the trend. And also we do see the potential using this high temperature stepwise drying to kill the insects. That will reduce the fumigation treatment in the future. Again, so based on what I have seen, I think I'm comfortable with about 1 cent per pound of the dry almonds for the energy cost. Next one, please. Okay, so this is what I see where this may go, but definitely we need to continue to do the study. When we using the off-ground harvest, we can do the sorting to separate into 2 or 3 different groups, and that's including in-hull almond, loose hull, or in-shell almonds. Then we can do the dehulling. When we only dry the in-shell almond, that will be ideal. We can reduce a lot of the drying time and also the energy cost. Then the wet hull can be used to produce a high-value product, such as a fermented feed. I think that could be a future to go. That's what I'm seeing for the future. Next one, please. I do want to thank all the people who contributed to the study, including my co-PIs. And at the same time, I do want to thank Guangwei. He has done tremendous amount of work in coordinating all the work, the tests. Thank you.
Okay.
My name is Erwin Donis Gonzalez. I'll be talking a little bit today about drying fresh harvested almonds in stockpiles. So Professor Chong-Li Pan just talked about his exhaustive work in mechanical dryers. In this case, it's an alternative to what he is currently proposing. Or also another step that can be taken to condition the almonds so that they could be properly dry with stadium type dryers or any of the suggested dryers that Professor Chong-Li Pan indicated. So as I said, my name is Erwin Donis. This project we've been working very closely with a master's student, Ismael Mayanga, who has been involved since the beginning of the project. And this project specifically is a collaboration between UC Davis and Dr. Michael Coates in Plant and Food Research. His name has been mentioned several times today, and we're looking at this pretty exhaustively. And I think that my computer here is suggesting that I just remove my last name. I don't know why my last name is blanked here. Anyway, I was going to ask all of you to just call me Erwin. I have probably the longest name in everybody here, so that's easier. So why was this so important? Basically, when anything that we were evaluating here in California, we could do the same in Australia. So we've been involved in this project for 2 seasons right now, but because of that, we have 4-season results. Basically, this has been very helpful working with the Australian team. What was the main goal of our project? Is to dry a reasonably sized stockpile within a reasonable time frame. And I will define reasonable later. That's why I have those in italic. What is reasonable, basically? And most importantly, to understand the airflow rates associated with both cooling and drying almonds as they are dehydrated. So what is reasonable? We know that today what we've talked is, regardless of the drying method that we used, either mechanical or something more informal like the one that we're proposing here in stockpiles, is if we don't use the conventional method of drying, dryers, farmers, or designated facilities, which have been mentioned, and I don't need to mention exhaustively anymore, would need to accommodate enough fruit so that the harvesting given day can be dried in a manageable state. By that, I mean between 6 and 12%. And it doesn't mean, I mean manageable, because stockpiles can serve as 2 different purposes. One, to dehydrate or dry almonds to storage levels, or 2, they can also serve to condition the fruit to further be dried in a different facility. This is actually a reality in very few facilities here in California, where people combine conventional sun drying with mechanical stadium type dryers. But most importantly, we cannot backlog or delay or disrupt the continuous harvesting process, which is important to the farmers. As examples of applications, here I have a picture of our in-farm stockpile. It's a mobile unit that we designed at UC Davis for the purpose of this experiment. But this could also be done in a commercial drying facility stockpiles, as it's a fairly flexible technique and quite mobile. So what were assumptions before we started this project? When I got involved with this project, is that or some ideas. There would be enough density in the almonds to distribute the air evenly without trapping, with our tarping. So we could blow air through the stockpiles, either in an A-frame or however we wished. And because almonds were dense enough, we could distribute the air quite evenly. The other idea was that opening a channel throughout the stockpile, like an A-frame or anything else that I'll show later on, or if you're familiarized with rice, for example, this is how it's done. Would allow this fruit to naturally breathe without any addition of fans or force or anything. And the third, but not least, is mechanical airflow will be augmented by natural airflow or natural drying, allowing a variety of fans to be used, and we could just basically use whatever we wished. So the first year when we got involved here in the United States, this is what we did. We designed this system that allowed us to go to any facility and dry almonds in a stockpile. The first year, we were just exploring the capacity of our system. This is a 2 horsepower propane heated vane axial fan. So if you're familiarized with xylose fans, it's quite used in those applications, but it's the smallest available in the industry. Again, it was meant for research purposes and not application of this. And we initially, even though we thought that ambient air could potentially dehydrate almonds appropriately, I used a combination of ambient and heated air. And the reason is because, as you can see, this was the latest variety, Monterey. So the weather did not allow, I did not feel confident enough to just dehydrate the almonds using ambient air. Because we were dealing with around 10,000 pounds of almonds, or 5 tons, the grower suggested that it was not feasible for him to just take any risk. We do measure the condition. We do measure the conditions within the stockpile on the fly, so we can make decisions if anything goes wrong, basically. But as you could say, this is quite time intensive. It took around 11 days, and basically to dehydrate almonds from an average of 12% to storage conditions of around 6%. And this was just an A-frame. As we could see right here, it was like half a foot A-frame height, with the almonds stockpiled over it, and there was just basically a hose blowing air inside of the stockpile. And this is what we basically found that year. I could here in the A figure, we have a relative humidity against time of all the drying days. The different lines are different layers within the stockpile. And this is the same, only that with temperature. I have temperature here in the y-axis in both Celsius and Fahrenheit for reference. But what we found, or the take-home message from this graph, is that differences in temperature and humidity between layers. As we can see here, this red layer is the bottom layer in comparison with a orange or middle layer, or a top layer, which has a darker orange. So the difference between that temperature and humidity reflects that there's a lack of appropriate air distribution and appropriate airflow rates throughout the stockpile. In other words, the system was stagnant and we weren't dehydrating to our full capacity. To better understand what was the effect of the airflow, at that point when I saw that that things weren't moving along quite well, we just wanted to evaluate what was the effect of airflow in the drying rate of almonds. And here we could see that the same variety, Monterey, at a much smaller scale, and around, basically, he was 5 cubic foot per minute per cubic foot of fresh almonds, 5, and here we have 90. So it's much larger, 90 CFM per cubic foot of fresh almonds. Here we could see that we could achieve desired moisture levels of moisture after 25 hours. So this scenario would be ideal to not disrupt the current harvesting methods that are being suggested. 11 days would have not been feasible. So after that first year, we understood that we had to either, one, have a smaller stockpile, have a larger fan, or potentially distribute air more uniformly throughout. This is the result for them in-bin dryer, differently to the previous. You can see that the lines from the top, middle, and bottom in the majority of cases almost overlap, which suggests that there's rapid humidity decline, there's a reduced drying time, and similar temperatures through layers indicate appropriate air distribution and airflows. But bear in mind that this is not feasible for the large-scale applications. But what's happening? What's happening is that we're experiencing what's called a drying front. And I'll use this schematic to describe what the drying front is. It is basically an invisible line in the product where air becomes saturated, or liquid water, at around 100% relative humidity. Let's say, for example, that we have an X amount of air, as we've shown here, around 5 CFM per cubic foot of almonds, of fresh almonds. We can see that the air does not have the capacity of removing that moisture, so moisture is captured by almonds within the stockpile. In our case, in the bottom of the stockpile, because the air was being blown through the top. But if we increase that, let's say, and this is just hypothetical scenario, just for example, 10 times, in our case, it was more than 10 times. It was around 15 times that we increased the air. But on average, we could see like it was like around 10. That tells us that now that air has the capacity of removing that moisture. And this can basically be controlled by either the airflow, which is controlled with fans and so on, and the depth or the amount of almonds or product. So when we saw that, another question that we did have as initially, or where assumptions were, is do we really need even this fans? Do we really even need heat? And in 2020 in Australia, we evaluated 3 different methods. One, 2.2 kilowatt fan, or this is around 3 horsepower fan, and in a range of different stockpile sizes, from 6,000 pounds or 3 tons to 40,000 pounds or 20 tons. Different kernel moisture contents at the beginning, and different treatments as well. As I said, here we have a 3 horsepower fan with closed ends, as we could see, to avoid the air from exhausting through the ends and being forced to the stockpile. Then we have a small fan, electrical fan here, which is just blowing air through the stockpile from the bottom, and another where we have no mechanical fans and we're just aerating with conventional ambient air. What did we find? In every single case, and this is just the example for the 20-ton or 40,000 pound nonpareil stockpile, we observed that there was a constant low temperature and high humidity indicating problems. What did this tell us? Is that we were going to see this, molds, presence of moisture potentially. Therefore, we did not want to take the risk of ruining or, the amount of almonds that we were dealing with. So the decision was made to turn down this after 8 days to reveal, as we said, the onset of mold from evaporating cooling or that wet front, as we've mentioned here. So what was the conclusion of this? Ambient air, especially in wet fruit, or not even that wet, we're dealing, like 14% maximum moisture content. Ambient air was not able to efficiently and effectively remove the moisture from the stockpiles, and therefore we observed problems. That same year, in 2020, we wanted to establish a better idea of what does that drying front mean. So we designed 2 different systems, a custom batch dryer and a cross-sectional stockpile dryer, which will enable us to study further that drying front, and it's actually current research at this point. In 2020, as we said, what was our concern? Can we distribute air? Can we have any sort of air distributor that can allow us to increase that rate of drying? As we said, that was one alternative. So we let our setup of our dryer the same way as in 2019, only that we added an air distributor that would force the majority of the air in the middle sections, because we know that the stockpile is taller in that middle section. So this is just a model of how that looked. This was built here in UC Davis as well. Here's a picture of that air distributor. It has a total of 12 outlets that distribute air accordingly to hopefully reduce the moisture content even further. At this point, we evaluated this air distributor with 3 different scenarios, or 3 different varieties: nonpareil, winters, and Monterey. 3 different sizes of stockpile, ranging from as low as 3 tons. This was an issue that we had with the harvesting equipment. Unfortunately, we wanted to make the larger stockpile, but we ended up with around 3 tons stockpile, or 5,700 pounds. And the largest stockpile with Monterey's around 7.6 tons, which in this case would be our worst case scenario. Highest humidity, largest stockpile, and ambient conditions, colder and more humid ambient conditions. So we were happy to have that as the largest stockpile. And what we learned from the previous years is that we had to use a combination of ambient and heated air to properly remove the moisture. As we could see here, what the air distributor allowed us to do is to reduce drying by around 50%. But we still, in average, have a 5 to 6 day, 5 to 7 window day of drying from any initial moisture content, regardless of the stockpile size. So this tells us that at this point, next steps need to consider expanding the size of the motors mainly, so that we can force enough volume of air through the stockpiles. As 6 days might be feasible in some cases for smaller scale growers, also might be feasible for conditioning fruit, but definitely not to completely dry fruits from their harvesting to the desired storage level. This is just a summary for the sake of time. I won't go through every single stockpile that we dried here in 2020. But as I said, you know, three different varieties, 3 different sizes, and the drying times were very similar between them. What is the cost? Professor Pan mentioned some costs regarding drying almonds using stockpiles, and he mentioned around 1 cent per pound. I apologize. In this case, I have all of my calculations around in dollars per ton. But here, just for reference, $2 per pound is 0.1 cents or 1/10 of a cent, while 18 is almost 1 cent. So $20 per ton is actually 1 cent. So we can see that in this case, the majority, and regardless, even the most energy intensive methods, which actually, because it's related to the weight of almonds, what we found is that the smaller stockpiles, of course, would spend more energy because we were blowing, or we were trying to force the same amount of air through it. But regardless, in our worst case scenario, we have ranges of below 1 cent or from 1/10 of a cent to a maximum of less than 1 cent to dehydrate a pound of almonds. I did not include the 2019 data, but as you can expect, if we compare it with the Monterey's, which is the same variety around the same time, by introducing the air distributor, we can reduce energy consumption by about 50%. So it was like 12 cents or around this area in 2019, and in 2020, the air distributor allowed us to do that. But what have we learned? First, most of our pre-2019 assumptions were proven incorrect. Open stockpiles would not circulate air unless it's forced using a distributor or using a fan or whatever we want to achieve. And this fan needs to be sized in accordance to the size of the stockpile. The A-frame or the tunnel, as we've called it, through the stockpile does not provide a pathway for natural air to circulate. And if we're just forcing air through one hole in that stockpile, the distribution of that air is not appropriate for the size of stockpiles that we're dealing with. Larger stockpiles at this point have proven to be uncontrollable drying fronts. So it's likely at this point that our next step, and this is what we are going to evaluate in Australia, is to switch to covered stockpiles that will force a central exit. Alternatively, better air distribution methods can potentially be developed as well. But this is how our test in Australia is going to look for 2021, or this is what it's painting for. One is a covered stockpile, as we can see here. So it's hard to observe this because it's not live, but this tarp is basically ballooned because the fan is turned on. This fan is 10 times larger than the fan that I have here. This particularly stockpile was around 50-ton stockpile with a 43 horsepower fan, heated fan. And basically what's happening here, what's being forced, is that this tarp is strong enough to not allow the air to exit to the top, but it's forcing it under the very nice blocks here, or trailer tires. So it forces the air through the A-frame, which is embedded here, or through the plenum, or through the void space or air frame. It forces it through the stockpile. Then that moist air returns through the stockpile and is exit to the bottom. So that's what we mean by back pressure, to reduce all of this spot molding or distribution of the air. So in summary, as I said, uncovered aerated stockpiles, which is what we have worked the most, require minimal infrastructure and can be mobile, but they can take from 3 to 6 times more larger than equivalently sized batch mechanical stadium or any type dryers. It requires multiple outlets potentially, or distributors, to evenly distribute the airflow and achieve the drying that we want to achieve. And has greater value potentially in conditioning fruit for alternative or other drying methods than just utilizing open aerated stockpiles for drying purposes. Covered aerated stockpiles, on the other hand, which we will be evaluating right now in 2021, seem promising. We are intending to trial a fairly small fan with a covered 20-ton stockpile, and then these larger fans that are going to be evaluated with much larger stockpiles, between 50 to 100 tons or 100K to 2,000 pounds of stockpile. And we'll keep you advised of what are the results from this next test. And with that, I want to thank industry specialists that have helped us in our research, students and staff, but most importantly, the California Almond Board of Guangwei and everybody there to working with us to better learn how stockpiles can be a potential way of dehydrating or conditioning almonds. Thank you.
Thank you, Erwin, and thank you all presenters. So we have a little time for questions, and then maybe Ashley, you want to start by reading some question left in the text box, message box. Oh, you need to unmute yourself.
Yeah. Okay, here we go. So we have a question from Alec, and it's talking about drying. So with drying facilities, was the assumption that the almonds needed to be transported from the drying facility to a separate processor? If so, what is the cost assumed for this?
Maybe Chris, you want to answer this, trying to say how your model works. Has your model included the transportation cost?
So for our model, we used as our template the relatively small number of Huller shellers that offer drying. And those are mainly in the Sacramento Valley to account for the risk of early rainfall. So in that case, there would not be a need for additional transportation. It's all consolidated within one site, and the costs are the sum total of everything that happens within the Huller sheller with regards to drying. That would account for capital recovery, operating costs, et cetera. So perhaps that will be a more common model as drying scales out, but you're right that there could also be these dedicated drying facilities that would warrant a separate analysis.
So Chris, continue on that question. In your the model, the cost of drying, you referenced the one of drying. It's about 3 cents, right?
It's about 2 cents per pound, which was the price quoted by these Huller shellers that offer drying.
Okay.
All right, thank you, Chris. Next question. How many commercial dryers are there in the state? And it says most are used for prunes and raisins and haven't been used in years. And then it says also the state of California moving towards getting away from using natural gas. What would be used as an alternative?
I think, I don't know if Tony, you can comment some. We haven't done survey, how many commercial newly available in California. Definitely, I really appreciate this question. There's so many available unused dryers from rice industry, from prune industry, from lots of industry. Those can be explored for our use if we get to the point. Yeah.
and it talks about going away from natural gas. What would be an alternative to it?
Tony, you wanna unmute yourself to make a couple comments?
Can you repeat the question again?
Yes, it's talking about also the state of California is moving towards getting away from using natural gas. What would be used as an alternative?
That's a really good question. Definitely, we do see the renewable energy is the direction to go for the environment. For right now, definitely natural gas is much cheaper than electricity, and everybody knows that. Definitely solar energy could be potential, and some other renewable energy could be used. I have to say I do not have a definite answer for this question. I do see the trend people want to use renewable energy for it. Thank you.
Thanks. So moving on to the next question. So what is the reaction of the growers in general to this method of drying? And will the industry be able to scale it up?
I think I can make a comment. I think this is we are look at the all aspect or benefit of pros or cons of alternative drying or alternative harvesting, including drying. Definitely drying is going to add a cost, add the burden in handling. But we also, from the presentation showing we have a benefit. We have much cleaner product, less insect damage product. We have a definitely cleaner product, less dust, lower dust from harvest, and also much less dust at the hauling shorting site. So we just want to present that, all information to growers, make growers to make a decision. This is just at the beginning, our exploration or research to show the pros and cons of alternative harvesting. Not going to involve lots of handling, involve lots of even some paradigm change in the harvesting practice or the handling. So we don't know how growers can do supportive of this, but if they have chance, some of those attendees of a grower have attended, heard the benefit from the alternative harvest. I'm sure they were open-minded to think about how to handle those, save them the cost and then create some benefit from Dr. Simmons' presentation. Yeah.
Guangwei, can I add some comments?
Yes.
Yeah, just like when we said, we are looking the potential of the mechanical drying from all different kinds of scales, from a laboratory to the commercial facilities. And you have seen from my presentation, we looked the different type of the commercial dryers. They could be potentially used. And so far, what we do see the feasibility, technical feasibility to using those available dryers for almond drying. And also through this research, I also understand the farmers' concern, because traditionally we just leave the almonds on the floor, let it dry, and it seems pretty simple and low cost. At the same time, when we look at the other tree nuts industry, from pistachios to walnuts, they all use mechanical drying, and also they work very well. That's why I see the potential in using mechanical drying for the almonds. Definitely, as Guangwei said, we need to think of the way fundamentally different to take this approach. Thank you.
All right, thank you. So we have a comment just talking about transporting wet almonds, saying that it needs to be looked at since the wet almonds do not flow out with the standard bottom dumps. And then also moving into another question, it says, how different is the drying temperature from ambient air versus the temperature during harvest?
Okay, I can continue to answer the question. So we have not really looked closely about the dumping. And for all the tests, we did use a large amount of the almonds to transport from orchard to the drying facility, but we have not seen anything say a big concern, and also depends how people load and unload it. I think that's the thing we need to consider. Then what's the second part of the question regarding the ambient versus the hot air drying?
Yes, it's just saying what is the difference between the ambient air versus the temperature during harvest.
Okay, I see. Okay, so definitely when we're using the ambient air, right, we don't need energy, all right? That is the saving from energy for heating, but it takes extremely long. As I said, it may take 3 or 4 days. So that uses a lot of energy to power the fan. That is the issue. So when we use the high temperature drying, we can short the drying time. Even we use the say for what we did using natural gas or propane gas, okay, to heat the air. But overall, the energy cost much lower than using the ambient air. That's what we found.
Okay.
Can I add to that answer? I think it also depends on the time of the year. When we start harvest, at least here in California, ambient air can be up to 100 degrees, 100 Fahrenheit, and during the day specifically. And at the end of the season with Monterey's, we have colder nights, probably like around even mid 60s and so on. So ambient air can vary quite significantly, while the temperature of the dryers, either the temperature of Professor Shonli commercial mechanical dryers or the stockpile dryers, can be controlled and increased to a desired level. At this point, in the case of the batch stockpile dryer, the maximum temperature that we were trying to achieve was 120 degrees Fahrenheit. And that we felt that was a good medium between protecting the quality of the fruit and the temperature for drying. So that answer to that question also, it depends on the ambient conditions at that point.
So maybe, actually, I think we almost...
Irvin says is correct. It really depends on the ambient air condition, and also depends on the harvest, the moisture. So what we did, we used the tunnel and did a side-by-side comparison, and the moisture, the initial moisture of the almonds was relatively high. That's the conclusion came from. Thank you.
I think actually we probably run out of time. If anyone you have a question, you can type in your question. We can follow up with you later on. But I want, before we close, I want to have Patrick make a short comment about your estimation about the slightly early harvest and followed by mechanical drying. You did some estimation on cost, like less pesticide use, hot rod stuff. That one you can give a little bit of illustration.
Yeah, just very quickly on the navel orange worm, I had extensive discussions with Dave Haviland, sort of our leading entomologist. 2 weeks early on a nonpareil eliminates an entire generation. Once you eliminate that generation of eggs on the navel orange, on the nonpareil, you then limit the generation of eggs and moths for all subsequent cultivars. Straight entomological modeling predicts that you will have a profound benefit on reduction of navel orange worm as a consequence of that 2 week early. And it's kind of interesting. You can go back 50 years to the work of Butel and Urio and Osagawa and Joe Ogawa. All of them have predicted that navel orange worm is a consequence of dry, open nuts on the trees. So clearly getting those off the tree early is an unequivocal benefit to navel orange worm. Haung rot also requires time for that fungus to infect that nut, that fruit on the tree, and time for that fumaric acid poison to move back into the spur. If you cut that time frame, you absolutely cut the Haung rot. So those two aspects, I think, warrant a little bit more investigation. But it's almost self-evident that both of those prominent pests will be mitigated by early harvest.
Okay, thank you. Ashley, go back to you. You have
Yeah, so on the screen right now, you're going to be able to see the QR code for CCA credit. And with that being said, you just go ahead and open the CCA application on your smartphone and scan the QR code. And once you scan the QR code, it'll ask if you want credit for this course, and you self-report it. But if you have any questions or anything, feel free to drop them in the chat. And I know, like Guangwei said, we did run out of time. There are some questions in the chat that did not get answered, but no worries. We will be passing that over to Guangwei and the speakers to make sure they get answered.
Okay. And then, first again, I thank all our presenters, and thank you for all of you to take time to sit in, listen to our webinar. Specifically, thank to some of our friends from Washington State University and the Michigan State University, also from attendees. Hopefully, we can reconnect it, talk about more, what your interest, if anything interesting you, any idea you can offer to us. And thank you all. And I think we're going to wrap up, close this webinar. We will have continually have in 2 weeks, we have other webinars. Hopefully you can call back in every 2 weeks.